chemical engineering paper, and the subject is heat transfer. The question is, a straight fin of uniform cross section and adiabatic tip has an aspect ratio length upon diameter of 4. If the Biot number based on radius of the fin as characteristic length is 0.04, the fin efficiency is dash percent. This is a numerical answer type question, and we have to answer on the basis of it, round off to nearest integer. So in this question, we have been asked to find the fin efficiency. So fin is you might know that fin is an extended surface that is used to increase the heat transfer. Okay, so basically, if I provide the fin, then provide the fins, then the heat transfer would be much efficient, and that would help in either more efficient heating, more faster and efficient heating or cooling, whatever is our main purpose. Okay, so there are two main parameters related to fin efficiency or effectiveness. So here they are defined as the fin efficiency is actual heat transferred divided by heat which would have been transferred if the entire fin were at base temperature of the body. Okay, so if my body's temperature is Ts, so at 100%, so yes, the heat that would have been transferred if the entire fin were at base temperature of the body. That means this entire fin should be at Ts. So if such is the case, my heat transfer would be very much efficient. And then the other performance factor is the fin performance. It is defined as the rate of heat transfer with fin and rate of heat transfer without fin. So in absence of fin, what would have been my rate of heat transfer? So that can be captured using this fin effectiveness. But in our question, we have been asked to find the fin efficiency. Okay, so we have to use this concept, fin efficiency. Okay, so we define this fin efficiency as NF is equal to actual heat transferred upon Q if the heat transfer of the entire fin were at base temperature. If fin is at base temperature. Okay, so in this question, we have been given a straight fin of uniform cross section, uniform circular cross section. So we are having basically we are having a cylindrical fin over here. And let's just consider that diameter of that fin is D and length is L. Okay, so here we have been given it has an adiabatic tip. That means no heat exchange occurs through this surface. So here delta Q is equal to 0, and we have been given L by D as 4 aspect ratio. And if the Biot number based on the radius of fin as characteristic length is 0.04, okay. Here we have been asked to use the radius of the fin as characteristic length. So that would become, so my Biot number is defined as Hx upon K. So it will become HR upon K is equal to 0.04. So later on we might be needing this, and we have been asked to fin efficiency. So for a cylindrical fin, you would have remembered the equation of the heat transfer if we are having a cylindrical fin. So that is given as under root of H. H is my heat transfer coefficient. P is the perimeter. So in this case, the perimeter will be pi d. Then K is my thermal conductivity. A is the area across which my heat transfer would. A is the cross section area. Okay, so it's the thermal conductivity of it. So area will become pi d square by pi r square. So that is basically pi d square by 4. So this is the first parameter, and the temperature difference. So if my fin is at if my wall temperature is TW and the ambient temperature is T infinity, then we can write it as TW minus T infinity, and then we have a factor of hyperbolic 10 ml. So you have to remember this formula for any of the fin, that is under root of HPKA, then the temperature difference, and 10 hyperbolic ml. So this is my heat transferred in presence of fin. Now heat the Q, if the fin is at base temperature. So for the idealistic case, it will be basically HA delta T, and the area of the heat transfer area would be this 2 pi RL. Okay, 2 pi RL is basically my perimeter into length. So okay, so that I can write it as perimeter equals to H into P into L, then my temperature difference TW minus T into. So this is my fin efficiency. So from here you can just cancel these terms. Fin efficiency will be given as sorry for that. Fin efficiency will be given as under root of HP KA upon HPL under root of 10 hyperbolic ml. So I think you can cancel this HP, so it will become under root of KA upon HP into 1 upon L into 10 ml. Okay, so we will be using this formula to calculate the fin efficiency. So yes, so from here you can see that this m factor is, we define it as under root of HP upon K. Okay, this is my m. So if we replace this under root of HP by K over here, then we can get it as 10 hyperbolic ml upon this will become 1 upon m, and this is 1 upon L already, so it will become this. So my final heat effectiveness factor is 10 ml upon ml. So you can straight away remember this equation for this fin efficiency. Okay. So what information we are having, the fin efficiency is given as 10 hyperbolic ml upon ml, and the other thing we are having HR upon K is 0.04. HR upon K is 0.04. The other thing we are having is L by D is 4. So to find this efficiency, let's just calculate this M first. Okay. So M is given as under root of HP upon KA. So for the fin, the perimeter, we discussed it as pi d, and area as pi d square by 4. So I will just replace those values over here. P is pi d, K into area is pi d square by 4. So pi will become cancelled. 4H d upon K. No, not this. So d will be denominator 4H upon KD. Okay, so now let's just find this ml term. ML will become length into 4 H upon KD. Now here we are having this HR upon K as 0.04. So from here we can get this HD upon K will be twice of that term. So basically 0.04 into 2 will be 0.08. Now I need to fit this equation over here. So what I will do is I will just multiply and divide this under term with diameter. Okay. So now I am having HD upon K. Okay, so this term I am having, and this d square I will take out of the square root bracket. Under root of 4 into HD upon K, I am already having it as 0.08. Okay, and L by D I am having it as 4. So 4 into under root of 0.32 is my ml. So you can calculate this, and the ml value will come around, I think, 2.262. We will put this ml value in this equation, and we can get effectiveness factor as hyperbolic 10 of 2.262 upon 2.262 is equal to, so this will come around 0.978 upon 2.262, so it will become 43 point, so it will become 0.4324, and we have been asked to write it in percentage, so our final answer will be 43.24%. So since we have been asked to round up to nearest integer, so we can write it as 43 or 44. So this will be my correct fin efficiency in percentage.